Okay, hello everyone. Thanks for joining the Lattice Developer Conference. The main objective of this training, FPGA power consumption analysis, is to go through the basics of FPGA power consumption and the tools available to you to have an accurate power consumption of your design. Obviously, if you have any question, please use the Q&A widget to submit it. We'll try to answer the questions at the end of this presentation. So my name is Murad Zakama. I prepared the content of this training and will be walking through it today with you guys. Currently part of the Lattice Insights training team as a content developer and training instructor. I have over 20 years of experience in the semiconductor industry, with which more than 15 years with Lattice and different responsibility, application engineer, field application engineer, and strategic account management. My main field expertise, the areas where I spend most of my time is on the Lattice hardware, software tools, FPGA architecture, design techniques, and best practices, as well as timing constraint. Actually, some of the sessions that we'll be presenting today are about timing constraints and some of the best practices if you attend any of these other sessions. In terms of academic background, I have a EE with a master's degree in microelectronics and an MBA in management, and from University of Quebec in Canada. Hello to all the Canadians on the call. So let's go through the agenda. So the agenda for the training has 3 parts. First part is a quick introduction in terms of power consumption theory and the power basics in FPGA. So we're going to start from the basics, and then we'll talk about power calculator tools. So there's a power calculator tool that is integrated with the Radeon or Daemon software platform. And it has different mode of operation. There is estimation mode, calculation mode, and simulation mode. So we'll try to go through all these 3 different modes. What's the difference between all these modes and how to use them? And most importantly, which one of them are more accurate or provide you more accurate information about the power consumption of your device. Then we will focus on the best way to estimate power with the lab on calculating power using the VCD file. We're going to see what is the VCD file and what is the simulation mode, how to use the simulation mode. So let's start with the introduction. So power consumption theory and power basics in the FPGA. So what is power? Not bringing something new here, but it's good to start from the basics of power, as the same concept applies to the FPGA world. So let's start with a statement from Wikipedia. I'm going to read it through, right? So power is the amount of energy transferred or converted per unit of time. In the International System of Units, the unit of power is watt or joule per second. The power for an electrical circuit is at a given time is defined as the voltage drop across a component multiplied by the current that is traveling through that component. So we'll see more about this, but the equation that kind of represents the power at the time t is the voltage multiplied by the current at a given time, where P is the power, V is the voltage, and the I is the current going through that component. So one of the questions that you may have, what impacts power? So these 3 factors that impact power. There's the temperature. So power consumption increase exponentially with temperature. We're going to see equations in the next couple of slides and how that is modelized. There's also the capacitance or the logic density. So logic density, when you have more logic, you have a bigger capacitance or capacitive load, then you have more charging and discharging. So there's more energy involved. The process technology also have an impact on the characteristic of the transistor, and hence the capacitive load that you have to be driving or changing a state for a transistor. There's another factor, what we call the transitions or activity factor, which represent the number of status change per clock cycle. So how many flip-flops or how many synchronous logic are changing at the same clock. Not all the flip-flop will be changing at the same time, but there's a percentage of them, and that will be represented in the activity factor, usually in percentage. So obviously, higher activity factor means more power consumed. So let's start with the impact of temperature change. So this is a graph that I extracted from the Lattice Power Calculator tool that represents the total power consumption for cross-link device over temperatures. We have in the y-axis the power consumption, and the x is the temperature. And as you can see, the power consumption increased exponentially with the temperature. So you can see at 17 degrees, for example, there is 14 milliwatt total power consumed by the device. But if the temperature is going to 68 degrees, or the ambient temperature going to a higher temperature, or 68 degrees, actually the die temperature, then we have more than twice the power consumption. So obviously, this behavior has been modelized with this equation that you see here. So the current is A is a coefficient multiplied by exponential B, another coefficient, and the temperature T. And the power is the voltage multiplied by this. So V multiplied by A multiplied by exponential B and T. These coefficients, so all the coefficients that you have here and other coefficients are calibrated with hardware measurements, and we're going to see how that is done. So in terms of the different component of power, there's mainly three components that you see in FPGA power consumption. There is static power, bias power, and dynamic power. So the static power related to the leakage current, it is consumed in absence of any activity, no active clock. It's actually what represents the device, configured device, with no active clock, and whatever leakage current represents the static power. So this component, what we call static power, is exponentially proportional to temperature. The bias power is related to the voltage that is applied to the substrate and is independent of temperature and usually associated with static power. It doesn't change with frequency. It doesn't change with. It's only dependent on the process node. And dynamic power relates to the design activity. So how many flip-flops are changing at the same time, either from 0 to 1 or 1 to 0. All these will be calculated or will be accumulated in the dynamic power. I mean, at a lower level, it could be explained as a switching capacitive load between different voltage states. So that's how we can simplify the reading of dynamic power. So if we look at the overall power calculation, or the power calculation for the overall device, so the total chip will be divided in a smaller component of different primitives that are used in the architecture, and all these components will have static power, bias power, and dynamic power. And for each one of these, we will calculate the current consumed by this component, and we aggregate all the different power consumption together to have the overall chip power consumption. Because you may have different components that are, using different voltages. So, and the calculation will become much more complex. So the equation that we see here represent the static power, which is the A exponential B and T, plus the bias current, or bias power if you multiply by the V, plus the dynamic power, which is C VF, and it's proportional to the frequency, obviously, and the power is V multiplied by I. So all these coefficients will have a process to get calibrated. So first, the initial coefficients are provided by the design group based on simulation model and based on block basis simulation model. So all these numbers are fed into the power calculator and correlated with the full chip simulation. Then once the silicon is back, the coefficients are adjusted to match the power characterization of the chip. So obviously static power is a fifth order exponential model. The dynamic power is linear model. And there's also what we call the worst case multiplier that are correlated with the silicon behavior. So we see the best case, the worst case, and there is a multiplier that will adjust or will multiply the power to have the worst case or the best case scenario in terms of power. And these are all integrated in the power calculator. So these multiplier factors, we're going to see that in the next couple of slides. So in few cases, we may have further revision of this coefficient if there's big discrepancy between what we see in the field and for some corner cases and what is in the software tool. But that's kind of the process, how all these coefficients get calibrated and get determined. So there's another factor that is also very important. So we have all these transistors switching, or all these resistor switching status. All this power is dissipated in heat. And there is what we call the thermal resistance that kind of define the heat transfer property of the material. So you have the die, you have the package, you have the heat sink, if there's a heat sink, and all these will have some thermal dissipation properties that has to be modelized. So we kind of determine how fast we can dissipate that heat from the die. So the theta, there is different value of theta or different ones, depends on which one you look at. So there's JC, which is the thermal resistance junction to case, and it's measured on degree per watt. CS, which is the thermal resistance for case to heatsink, if there is a heatsink that is used. The thermal resistance junction to board, because the device is soldered on the board, there is some heat that is dissipated through the board also. And there is a case to ambient. So in case you have no heatsink, there is a thermal resistance for the dissipation of that heat from the case top to the ambient environment. And there is the thermal resistance junction to ambient, which is a collection or addition of thermal resistance junction to case and case to ambient to determine the junction to ambient thermal resistance. So, and once we characterize all these thermal resistance, and we have this, I mean, this will vary, depends on the package, depends on the board, depends on multiple factors, then we can determine the junction temperature, which need to be in a safe operating mode, depends on the type of device that you are using, commercial, industrial, automotive. And it's the ambient temperature in case of you are using junction to ambient, thermal resistance junction to ambient. Then it's the TA plus junction to ambient multiplied by the power using the ambient temperature. Obviously, if you are using the case temperature, then it's a junction to case, and then the temperature of the case plus theta junction to case multiplied by the power. In the case you are using the board temperature, then it's temperature of the board plus the theta GA multiplied by the power. So that's how the junction temperature is calculated. And why that is important, because the junction temperature should not exceed certain value, otherwise it impacts reliability of the device, and it impacts the operation of the device, and it goes outside of the characterized device spec. So power calculator allow you also to estimate this value of theta. I mean, in some cases you may have your own environment. You may do your own simulation to determine this thermal resistance. If not, you can select certain value in the power calculator to determine the theta or the tool will determine that for you. So if you have the terminal resistance, you can define here, you can select this option and it will allow you to enter the terminal resistance of your system. Otherwise, then you use, select the board type, the heatsink, if there's any heatsink, the airflow, and then the effective data junction to ambient will be calculated automatically by the tool. So if we take a look at the Power Calculator tool and terminal profile, so if you click on the terminal profile, you're going to have this window that we've seen in the previous slide. And then by selecting the option of that you have, whether using the terminal model or using your own defined data, then different window will be available to you to be populated. If you use the terminal model, then you have to select the board selection, the heatsink, the airflow, and so on. And the board size matters, and it's not the same thing that you have if you have a small board or a larger board. So the smaller board have tendency to lower terminal resistance and will be much harder to dissipate the heat. So all these factors will impact the heat dissipation of the device. So once you've done all that, then the tool will calculate the power based on an ambient temperature. So you define your ambient temperature. Then the data will be defined by the information that you provide here. Then the junction temperature will be listed here. So calculated junction temperature, in this case, is 25.64 degree. And it will also provide you what's the maximum safe ambient temperature based on the design that you have and the loaded in the Power Calculator. So all this information is calculated by the Power Calculator. So now that we covered the principle of Power Calculator, how the power calculation is done, so let's go into the Power Calculator tool and go through the different mode that are available. So estimation mode, calculation mode, and simulation mode. And the same equation apply in any mode that you have. So the same equation that we have seen in the previous slide will be used whether you are in estimation mode, calculation mode, VCT mode. So what's different, okay? So the difference is the input that you have to the Power Calculator. So in estimation mode is usually early in the design. You may not have a design already, but you know kind of the rough idea about the resource utilization that you may have in that design. So you go to estimation mode in terms of estimating power calculation. The calculation mode is part of the software design flow. So it uses information from the software. I'm going to see that in the next couple of slides. And simulation mode, you can actually import simulation data in order to estimate the activity factor that you have in your design. And we have more details later on that. So, obviously the terminal profile can be set based on your design preferences on your actual design and the data that you enter or the characteristic of the board that you have. So let's start with the estimation mode. So estimation mode, it's like I said, it's very early in the design. You may know that you're building a design that may be using 10,000 lookup table. It has 10 block of RAMs, 5 clocks, 50 IOs, and so on. So you enter all this information into the Power Calculator without having any source code HDL to back that information. So user will have to estimate all the resource utilization, the activity factor, and the clock frequency for all the clocks that you have in your design. Obviously, the data provided by the Power Calculator will be as accurate as the information you provide. And usually, this is the least accurate power estimation that you may have to use because all these information are estimated by the user, not accurate. They are not related to a specific design. So in calculation mode, it's a little bit more elaborate. You actually have a project. So you created a Diamond or Radiant project. you have your HDL code that you wrote already. You synthesize the HDL code. The HDL code, when it gets synthesized, generated the UDB, which is a unified database. And then going through the map, so all the components are mapped and selected, and the packing is done. Then you go through the place and route, and you have a UDB file after place and route. So this is the exact representation of your design, including routing resources, the exact number of lookup tables or logic cells that are used, the clock frequencies, the different clocks that you have, the different IOs with their voltages. Everything is very accurately represented in the unified database. And you can even input the timing information. So how fast the design will work will get imported automatically to the Power Calculator. So obviously you have a very accurate representation of your design using the Power Calculator in calculation mode. And the only variable or only information that need to be estimated by the user is the activity factor. So we're going to see more about the activity factor later, but that's still a user input. So this mode is a better accuracy, like I said, the only factor that is user estimated is the activity factor. So the simulation mode or advanced calculation mode is a step further in terms of the power estimation. So we have the same exact information as in the calculation mode. So we have our design with the UDB file, which represent all the connection, all the resource utilization. We have the TWR, which represent all the frequencies for all the different clock domains. But we are using calculating the activity factor from simulation. What we actually do is have a test bench and record all the activity that are done in your design and import that to the Power Calculator. So the Power Calculator can have a very accurate reading of the activity factor, which make this mode is the most accurate as all these Power Calculator input information are extracted from design and simulation file, and they are not estimated by the user. Okay. So just to summarize, so these are the three different modes, so estimation mode, calculation mode, and simulation mode. I would say, though, that the power estimation is as good as the accuracy of the input data, and we've seen going through estimation mode, calculation mode, and simulation mode that when you are in estimation mode, everything is estimated by the user. That's least accurate. We have much more definition in calculation mode, and in simulation mode, we have a very accurate representation of the design, even including the activity factor. So let's get into the details of the activity factor. So what is activity factor? So activity factor is defined as the average number of signal transition per second. So a transition could be a change of status from 0 to 1 or from 1 to 0. There is two types of activity factor. There is the synchronous logic activity factor, and there is the combinator logic. So let's start with the synchronous logic activity factor. So in the synchronous logic, what we need to know is how often the output changes relative to a clock. So let's take the example of a 2 or 3-bit counter that we have here. So the bit 0, bit 1, and bit 2, we can see the bit 0 changing every clock cycle. So this is 100% activity factor. Bit 1 is only changing at every other clock cycle, and bit 2 is changing every 4 clock cycle, which is 25% activity factor. So the activity factor for a 3-bit counter, if you do the average of all these numbers, we have activity factor of 58%. Okay. If we take another example of 18-bit counter, I'm going to go to that later on in the presentation, then we end up with an activity of 11%. So it's really dependent on the design. The activity factor could vary depending on the design. On the other hand, when we talk about combinatorial logic, it's very hard to predict the activity factor. So we should avoid as much as possible any combinatorial logic in the design, because combinatorial logic could create, the timing of combinatorial logic is not predictable and could create glitches. And even though that is a glitch, it's a change, it's actually a change of status. So design can go from 0 to 1 or 1 to 0, and that will create power consumption, or would translate in terms of transition and power consumption. An activity factor in combinatorial logic could be even higher than 100%, because these glitches could be higher than the frequency. So relative to the frequency, they could be much higher than the frequency. So it could be over 100%. So it's very hard to predict. So general recommendation, avoid to have combinatorial logic in your design. Try to synchronize everything to a clock. So the in general, so just a high level overview. So potentially high activity factor would be adders, arithmetic logic, XOR gates, forward error correction. And potentially low activity factor would be control logic, power sequencing. These are usually things that don't require to switch a lot. So activity factor associated with them will be very low. So as a note here, so activity factor is a rough estimate that depends on the design and can have a high impact on power estimate. So you've seen in the 3-bit counter that for the bit 0, it's 100%. For a bit 3 is 25%. For a 18-bit counter, the activity factor, the average activity factor is 11%. So there is a big difference between having activity factor set to 11% and set to 20% or to 10%. On average, so statistically on average, the activity factor should be around 10%, from 10 to 20%, but it's really dependent on the design. The default value on the power calculator is 10%, but you can change that to whatever desired value. So the question that you may have, so okay, what's the best way to have an accurate power estimation? So the answer to that will be simulation-based power estimation using the VCD file. Now, what is a VCD file? Okay, so we're going to go through that in the next couple of slides. So a VCD file stands for value change dump file. It's actually a dump file where we put all the transition that you have in the design. It's an ASCII file format that is defined by the IEEE standard and allows the simulation tool, ModelSim, for instance, to record the signal changes of value that you have on the board based on simulation test bench, and allow you to have that information available to be used in the power calculator. So these other files that may be used in the industry, like SAFE files, SAEF file, which is a subset of a VCD file, and it is actually generated from the VCD file. It contains a summarized version of the VCD file, and the power calculator, Lattice Power Calculator, only support VCD file. Other vendors support different files. So like in AMD Xilinx, they support both options, VCD and SAF, whereas in Altera, they support only VCD file. Intel Altera support VCD file. So in terms of the VCD file format, so it is, like I said, based on simulation. It's based on RTL simulation that you run through a simulation tool. And it has multiple sections just to you get a high-level overview of the content of this file. So there's a header section that has the date, the file creation, the tool name, and so on. So that's the header section. Then there is the variable section, which represent all the signals that you have in your design that will be listed in the variable section. And the data section, which will represent all the transition with the timestamp associated with all these transitions. So that's how this file is constructed. So how do we generate a VCD file? So the first thing you need to do is run a simulation on Lattice Radian or Diamond using the simulation wizard. So you could even open ModelSim on standalone or any other simulation tool standalone. Do your simulation environment, compile your design, add the waves, run the simulation to verify the logic. And then you must restart the simulation because the recording will happen at the time 0. So we need to restart to capture all the signals toggling, or record all the signal toggling. And then create a VCD file. So with the command VCD file and the file name.vcd are the signals to dump into the VCD file. So the path to the instance and the star if you want to include everything. Run the simulation for a certain time and then stop the simulation so the file get closed and recorded. All the transition or all the VCD file information will be closed and recorded. So a very simple example of a VCD file generation script will be as simple as this. So you have your simulation environment started. You do like a do file if you want to restart -f, then VCD my VCD file.vcd, VCD add the test bench UUT, include everything, run for 1,000 nanoseconds, then quit sim, and then you have the VCD file with all this information. So you could have more complex VCD file generation, but this is kind of a simple example that I want to list here. So in order to integrate the VCD file into the Power Calculator, so you have to open the simulation file. So there's an option to integrate the simulation file into the Power Calculator. So open simulation file. Once you do that, then it will give you an option to have VCD file referenced. And once you click OK, the Power Calculator will go into calculation mode of all these transitions to calculate the activity factor for each one of the blocks based on the simulation information. So let's take an example. I mean, a lab, but I'm going to go through the lab. So I have created a Lattice Radian project, and I can share with you the source code if required. You can request that, and we'll be able to share this lab. Open Power Calculator in calculation mode. Then verify that the constraint frequency has been transferred. Obviously, when you do open the Power Calculator, it will ask you if you want to import the timing constraint that you have. You want to use the Fmax that is generated by the tool, or just the timing constraint that you have in your design. Then took note of the power numbers, so the total static and dynamic power. So I populated all these metrics, and you're going to see that in the next slide. Then I'd gone to simulation mode. So I ran the simulation with Radian, generated a VCD file and imported into the tool, and then have the simulation mode VCD information populated here. So, and then compare both side by side. So obviously, when you do calculation mode, the default activity factor is 10%. So that's how I use it. For this specific design, I have a very simple 10-bit counter. So I have a clock reset and 10-bit counter going out. And that's the design that I have gone through for this example for this lab. So this is the information that I extracted. So in calculation mode, I have activity factor of 10%. Static power 20 milliwatt, dynamic power is 20 milliwatt, and total power of 41 milliwatt. When I've gone through simulation mode and used the VCD file, I did the simulation. So the activity factor came up to be 19.95%, not 10%, because as we've seen before, if you have a 10-bit counter, the activity factor will be higher than just 18-bit counter or a different size of counter. So now I'm ending up with a 61 milliwatt power consumption versus 41 estimated by the power calculators. They are all generated by the power calculator. So the difference is so big, but that's mainly related to the poor estimation of the activity factor. So that's why that input is very important, and most of the discrepancy between real activity factor, real power consumption into the device and the calculated one may come from the poor estimation of the activity factor. So if we go into the details of the power calculator, we will be able to extract all these data. So in the calculation mode on the top and the VCD mode on the bottom. So you're going to see that we have the 150 megahertz clock frequency. That's what is received from the tool. The activity factor is 10%. The EF is actually the effective time that the block is on. So we have some blocks that could be put in shutdown mode. So and you could add that in here with the EF percentage, the number of lookup tables used, number of register, and so on. And for this, for the calculation mode, that's the power estimated. In the estimation mode in calculation mode through simulation, we have the same thing, 150 megahertz, but we have the activity factor that is calculated by the tool is 19.95 megahertz percent, and the power calculator power for that specific block. The same thing for input and output. So you have the activity factor 10% here with the frequency, toggling frequency. In the calculation simulation mode, we see that the activity factor is 24%, whereas the 24% for the IO, and we have 0.28%. I mean, can anyone guess why we have an activity factor of 24%? We should have 19.5%, right? So if you pay close attention, you're gonna see that the IOs, they are all the same standard, but they are split between two banks, bank 1 and bank 2. And in bank 1, in bank 2, probably we have the MSB because it's toggling at very low frequency. Sorry, slide. So toggling at very low frequency. And all the other bits are in the bank 1. So in bank 1, we have a higher activity factor, but if you do the average between these two, you should get to the 19.95%. So let's see more in terms of theoretical calculation of the activity factor versus the calculation mode or the VCD mode that we've seen. So we have a table here that I've done in Excel with a number of bits of a counter, so 1 bit to 18-bit counter, the bit number, and the toggling activity factor. So bit 0 is 100%, 50%, 25, and so on. And I calculate the average activity factor. So obviously for a 10-bit counter, so we have 19.98% activity factor. So in calculation mode, we've seen that we get around 40 milliwatt. But if we do the VCD mode, we get around 60 milliwatt of power consumption. And the calculated activity factor using the VCD is 19.95, whereas the theoretical one is 19.98. Any guess why we have that small, tiny difference between the two? So I'm going to answer that, and you're going to think about it afterwards if you want. So when you do a VCD mode, in the design, the test bench that I have a reset signal that goes for a certain time before releasing the clock to start releasing the counter to be start counting. So all that data is recorded. So if you run the simulation long enough, these 19.95 should get towards the 19.98. Or if you have no reset, you should have the same number. But since we have a reset signal, some of the signals that are recorded by the simulation are zeros, which lower that activity factor. So that's the main reason we have the difference there. So, and just go back one point on this slide. So the importance of having a test bench that represent the true activity of your design is critical to have a true representation of the VCD based activity factor calculation. And the reason I'm saying that, sometimes we do test bench to test corner cases of our design. And that may not be truly representing the real activity of the FPGA or real operation of the FPGA. And in that case, we end up with activity factors that are misleading. And remember that the power calculator output is as good as the input to the power calculator. So if you have wrong data input, then the output will be as wrong as the input data that we have in there. So in terms of reference document, there is a lot of reference document that you can go to have more details about this subject. So these technical notes. So we have power management and calculation for crosslink NX device technical note 02075 that is available on the web, on the Lattice web. The same thing for Certus, Certus Pro NX, Mac XO. These technical notes available for more details on this subject. Thermal management technical note is another document. You'll find some details in the Nexus family datasheet or any device datasheet also about this subject. And the Lattice Insights training portal, it's the official training platform for Lattice ecosystem, including software, hardware, and solutions, evaluation boards. You can sign up for free, and you'll have access to pre-recorded video. You can even request some instructor-led type of training. And Radian help. So with the tool Radian and Diamond, there is a help integrated that allow you to get details on the power calculator or the different functionality that are available to the power calculator. So, and these are some examples of the courses that are available in Lattice Insight. So power calculator, power optimization techniques. We have actually a session on power optimization also. Please sign up for that. Ultra low power product line overview, accelerating low power with embedded vision. So there's multiple courses. I try to gather some of them here so you have a reference point. So in terms of summary, so we've seen that FPGA power consumption is impacted by temperature, process node, and activity factor. We spend a lot of time on activity factor because that one is hard to predict and depends on the design, provided some different ways of using the activity factor. Static power is exponentially proportional to temperature. Dynamic power is linearly proportional to switching frequency. We've seen also the power calculator 3 mode of operation, estimation mode, where you can use it early in the design before any HDL that is constructed or written, any source code. Calculation mode, good accuracy. I mean, you can use it based on activity vector that you define. and simulation mode, which is the most accurate and provide the most accurate information about the power calculation. And remember, power calculator is as good or as accurate as its input data. So garbage in, garbage out. So depends on how accurate the information you input to the power calculator, you will get the higher accuracy if these data are well defined. So that brings us to the Q&A session. So if you have any question, please put it on the chat on the Q&A widget, and we'll try to answer all these questions. So let's see if we have any questions here. Okay. So the obvious question, obviously. So what's the accuracy of the power calculator? And I get this question all the time. So what is the accuracy of the power calculator? How accurate is the power calculator from Lattice? I mean, it's a hard question to answer. And honestly, I mean, after going through all the details that we've seen in this presentation, I think you can understand the complexity behind that and the way the power calculator works, and it's as accurate as the information that you input. It depends on multiple factors, which mode you are running. The power calculator is in estimation mode, calculation mode, or simulation mode. Even in simulation mode, how accurate is your test bench compared to the actual behavior of your design in the field or in on the board? So given that you have accurate input to the power calculator, you should have a very fairly accurate estimation of the power of your device. So another question: is it recommended to use heatsink to lower power consumption? Yes. I mean, I think we've seen in the presentation that the static power increases exponentially with temperature. So having a heatsink will improve the thermal dissipation of the device or of the silicon and lower the operating temperature, which should improve the power consumption. We usually use heatsinks to avoid having the chip go outside of the operating range and impact reliability and so on. If the operating temperature is low enough, you don't need a heatsink. Actually, in most of the Lattice devices, there's no heatsink that is needed. In 90% of the time, you don't need a heatsink. They are designed for low power, and there is no extra money that is needed to put a heatsink on. Another question about the accuracy. So what is the accuracy of the power calculator in simulation mode? So I think I answered this in the previous one. Again, it depends on the test bench and how that is representative to the actual behavior of your design in the field. So another question, lab number one. So why do we see a small difference in static power between calculation mode and simulation mode? That's a really good catch. Thanks for asking that question. And I mean, that's a good catch. So just going back to that slide here, yes, so you see that static power is 20.267 in calculation mode, whereas in simulation mode is 20.318 milliwatt. I said they are both the same, yes, but they are very close. So, I mean, the way to explain this small difference is by having a higher activity factor. So higher activity factor means there is more heat dissipation, and the temperature, the die temperature will be higher. and that has a small impact on the static power. This design is very simple, so there's not a big impact. But if there was a bigger design and there's a big difference in the activity factor between calculation mode and simulation mode, you're going to see a big difference here. But that's a good catch. Thanks for that question. And the question, how do you estimate activity factor for a specific design? I mean, it's really hard to say. It's really dependent on the nature of the design you have and the type of logic you have. But I mean, in this case, we rely more on statistic, and it's statistically impossible to have a design running at 100% or 0% activity factor. So based on the benchmark we've done on multiple designs, and average activity factor is usually around between 10 and 20%. So if you have an activity factor between 10 and 20%, you're in the safe range. 10, 20%, 25% probably for extreme cases. But if you have that activity factor set in the power calculator between these numbers, you should be good. There's other questions, but I think we will take note of all of these, so and making sure that we stay within the time budget here. I'll take note of all these questions and get back to you on all of these. Thank you very much. Thanks for your time. Thanks for your attention. Hope it was useful. Bring some insight on how Power Calculator tool works in FPGAs, and looking forward to see you in other sessions. Thanks.